All right, everyone, thanks for joining us today. We are SP. Today we'll be presenting to you our plan for the large-scale production of PHA bioplastic from crude glycerol. So this is our team.
I'm Charles Doyle.
I'm Ryan Gilboy.
I'm Feng Lu.
I'm Charles Lee.
And I'm Bradley Mack.
So here's our agenda for today. What we'll be talking about, we'll first introduce our background and kind of the problem that we have, followed by our vision statement. We'll then go into our process design detailed, followed by some safety considerations and our layers of protection analysis, after which we'll talk about our financials and end with our conclusions with questions in the time remaining. So starting with our background, I'm sure a lot of you are already very aware of plastic accumulation in our environment, particularly macroplastics, where you can visibly see trash piling up on beaches and such like that. However, we are now beginning to realize as a society that microplastics, plastics that are less than 5 millimeters in size, are actually starting to seep widespread into our environment, with one study finding in the North Atlantic that 70% of marine life has microplastic within them. So while studies on the effects of microplastics in humans are pretty scarce right now, there have been some studies that have shown the negative effects of microplastic on marine life. So as we as a society are moving forward towards a more earth-friendly approach to manufacturing plastics, we'll be looking more towards biodegradability as well as mitigating the amount of petroplastics that we're releasing to the environment. As such, bioplastics in particular are seeming to be an emerging alternative to petroplastics. And you can see in this chart over here that the distribution of the various types of plastic that were found in some of this marine life that I was speaking of. And a huge percentage of this is actually polyethylene, and we'll be talking about a possible alternative to that. So our product, PHA bioplastic, which stands for polyhydroxyalkanoates, it has similar material properties to polypropylene and polyethylene, in particular having a similar tensile strength to polypropylene. It's completely biodegradable in various environments such as soil and compost, degrading to CO2 and water. And it's produced by many strains of bacteria as an energy storage molecule, much like starch in plants. Another product that will be produced in our process that we'll describe later is 1,3-propane-diol. This is derived from our first stage, our glycerol fermentation, and has various industrial uses as antifreeze, as adhesives, as well as a solvent in the feedstock.
You kids packed a lunch, so I'm taking you to Wall Street for the market analysis. So right off the bat, you can tell, pretty easy to tell that we're going to have two markets to compete in. So we have two products. We have PDO and PHA. But the PHA, our bioplastic, is going to have to compete with other bioplastics and traditional petroleum-derived plastics. So our direct competitors are going to be PHA producers such as BioAmber, BioMaterra, Full Cycle Bioplastics, and then the indirect competitors are going to be like polyethylene, polypropylene producers like Dow Chemical, ExxonMobil, Chevron, big names. And then our PDO competition is DuPont Tate. It's the #1 producer. Produce a whopping 63,500 tons a year. And so the prices, the price of PHA is what's keeping it from being a widespread alternative for traditional plastics. You can see it's about 4 to 5 times the cost of traditional petroleum-derived plastics. And so our goal is to really drive this price down and pierce through the market. Then our 1,3 PDO is just going to be sold at traditional market price. And so the market value. So the market value for PHA is about 13,000 tons as of 2016, and it's expected to reach 17,000 metric tons by 2021. We plan to only produce 1,000 metric tons of PHA, so we're in no worry of violating any antitrust laws. And Our global market for PDO is about 134,000 tons, which we plan to produce as a byproduct is around 5,000 metric tons. So our strategies, we are going to be, we're going to form ourselves as a corporation in order to allow for easy investment to fund our fixed capital costs. We hope to be located in Goshen, Indiana, where we will sell PHA to Berry's Plastics. Our plan for that is to sell at a high price for 7 years in order to cover our fixed capital costs and pay back our mortgages, loans, whatever else we need necessary in order to start our company up. And then we're going to cut the price to be competitive with polyethylene, polypropylene, which I'll go into more detail in later. And we just plan to sell the PDO to Dow DuPont in Michigan, another benefit of being located in Goshen.
All right, to kind of sum up our company's vision statement, at SP we intend to promote the adoption of bioplastics over petroleum-based alternatives to mitigate the accumulation of non-degradable plastics in the world's ecosystems and food supplies.
So we're going to dive a little deeper into the weeds as to how we plan to produce our PHA. So I want to give you kind of a brief overview of our process to begin with, because it's kind of a complicated system we have here. So first thing we have to do is we have to take our crude glycerol, which is our feedstock, and we're going to be fermenting that in a CSTR in order to produce volatile fatty acids. These volatile fatty acids are the actual substrate that will be creating our PHA bioplastic. Another product of this fermentation is the 1,3-propane-diol, which, as you saw earlier, is actually a fairly valuable co-product. So what we don't want to do is allow the 1,3-propane-diol to be consumed and turned into PHA, which may happen. So the way we plan to prevent this is we're going to be conditioning our cells using a sequential batch reactor in order to not consume our propane diol, and we'll go more into detail on how we plan to do this. So after we achieve our conditioned biomass as well as our volatile fatty acids, these two will be combined in our batch reactor that will actually be producing our PHA bioplastic as well as retaining our 1,3-PDO. So what kind of makes our process special is we're going to be using a mixed microbial consortium, which is a collection of various different bacteria. They are generally derived from wastewater sludge. And as you can see in this chart here, this was derived from one of the main pieces of literature we used to come up with our plan. And there are two primary genuses that are involved in the production of PHA, Americoccus and Theora. And this was actually from a wastewater treatment plant from Denmark, because that's where some of the researchers were based. So we'll go into how we plan to get our MMCs in Goshen. So some of the advantages of MMCs are that they offer stable and high productivity while also being highly resilient to any contamination, particular contamination that we might see in our crude glycerol. And because we have many different species, this also helps add another layer of protection from potential single strain extinctions.
So here we have a detailed process flow diagram of of our process as a whole. Important things to note on this diagram: these three reacting vessels represent the three main stages of our process. So the fermentation vessel is up on the top left, the SBR enrichment vessel in the bottom, and on the far right is the PHA accumulation vessel. I'm just going to talk a little bit about some of the process control elements we plan to implement. So on the enrichment vessel and the accumulation vessel, we just have simple control loops that are regulating temperature, level, and gas composition, as we're going to have like a gas sparge going up through the bacterial mixture. But on the fermentation vessel, we want to have a higher degree of control for temperature, so we're implementing a cascade control loop with the cooling jacket water flow rate. So we'll have a flow controller that gets a signal from a flow transmitter that acts on the cooling water flow rate valve, but also receives an input from our master controller that reads from a thermocouple. So to save cost on some of the water that we plan to use, we were looking into using just river water, as we don't expect these reactions to gain a lot of, or to have a high exotherm. So river water as a source may have some disturbances in temperature. So we were thinking that to maintain a nice 30 degrees Celsius temperature, we would use that cascade control system. Another thing to note is that pretty much every valve on this diagram is fail closed except the effluent valve off the fermentation vessel. As it's a CSTR, we didn't want anything overflowing there. That leads into a very large effluent tank, so our thinking was that having it fail open would remove the possibility of overflowing while just safely storing in a vessel that we can obtain material from later on. Everything else is fail closed to ensure that bacteria does not build up in the system later on downstream. So now I'm going to talk a little bit more in depth about each of the three main process steps, starting with the fermentation. So our feed for the fermentation vessel is going to be crude glycerol, which, if memory serves me, was priced at roughly 3 cents per gallon or kilogram?
Pound.
Per pound, okay. So it's a very cheap feedstock. We expect to have roughly 70% purity by weight. So in the fermentation vessel, we will mix this crude glycerol along with basic anaerobic growth medium, which is just some pH-balanced, salt-filled aqueous solution, as well as some anaerobic mixed microbial consortia sludge that we plan to source from a wastewater treatment plant in the area. So while in the reactor, bacteria will break down the glycerol through a complex fermentation pathway and produce lactate and acetate. Lactate will further react down into some of our VFAs, which include butyrate, propionate, valerate, and acetate as well. So we would use up the feed stream at a rate of 110 grams per liters per day of glycerol, and the effluent stream would have an estimated rate of 38 grams per liters per day of 1,3-PDO and 11 grams per liters per day of butyric acid, which is just the acidic form of butyrate. So while we do have small portions of propionate and valerate and acetate, butyrate has been shown to be kind of the driving force in PHA uptake by bacteria. So that is kind of the metric that we are concerned about moving forward. So in addition to the continuously operating CSCR fermentation vessel, we plan to have a PHA enrichment vessel operating simultaneously. And here we condition bacteria to primarily use VFAs to form PHA over 1,3-PDO. As mentioned in the market analysis, 1,3-PDO is a high-value product in and of itself, so we would rather have VFAs converted to PHA instead of that 1,3-PDO. We would do this by having a reactor operate in a feast-famine regime. So the feast regime will have an inlet of some glycerol, VFAs, basic anaerobic growth medium, and both anaerobic and aerobic bacteria would be fed VFAs as the only feedstock. And over the course of one feast cycle to a famine cycle, the famine should kill off any bacteria that did not use VFAs as a feedstock. And over the course of many cycles, the bacteria can actually be conditioned to have a higher affinity for VFA as a food source. This vessel would have an 8-hour hydraulic retention time, but that really involves just 4 hours, after which we remove half of the biomass and then feed that half conditioned biomass into our next process here. So this is where we have conditioned biomass from the enrichment vessel and the fermentation effluent meeting in this accumulation vessel. So here you have conditioned bacteria, you have VFA-rich effluent and 1,3-PDO from the fermentation vessel that come together. The bacteria use the VFA to produce PHA while leaving the 1,3-PDO at a very high purity. So the cycle time of this is also 4 hours, which lines up fairly well with our enrichment vessel. And our expected product stream would have a composition of roughly 13 grams per liters per day of PHA and 36 grams per liters per day of PDO. Our product stream is going to be a mix of biomass solids in which the PHA is encapsulated, as well as a liquid 1,3-PDO stream. So we would send that downstream for further processing.
So for our proof of concept, we decided to go with a simulation since we were unable to getting access to a lab that kind of worked with biologics in this kind of area. So for our simulation, we decided to use Aspen Plus, but because we've used it in the past for Capstone 1 and we have some experience with it. However, Aspen Plus does have limited biological processing, so in terms of our simulation, we'll kind of be ignoring that SBR cell conditioning step, but it does allow us to have some access to polymer reactions where we'll take the volatile fatty acids and convert them into PHAs. And in terms of our actual chemical reactions, there is limited kinetics data found in the literature that we looked at, but essentially all of them are essentially a zero order reaction that is based on the MMC. And we would have liked to do possible further simulation in SuperPro design for the bioreactors, but due to time constraints, we weren't really able to look into that. So for our Aspen Plus simulation, mass balance is, as I mentioned before, we essentially just look at the CSTR in the batch reactor and kind of ignore the SBR for biological conditioning. So essentially we just have our glycerol stream feeds into the CSTR, which produces our VFA stream. In this case, it converted 100% of the glycerol, which is similar to our 99% that we found in the literature, and converts to the product stream at the end. And one stream that's kind of missing there is an oxygen stream to convert the volatile fat acids to their PHA conversion, which is essentially just the increase in mass there.
All right. All right. So I'll be going over the safety considerations for our process. So luckily, all our chemical components are relatively inert, non-reactive, especially the glycerol and the PHA. They're basically food for cells. So if they're in the environment, cells would take them out and break them down to safe components. The more volatile, the more dangerous, high-risk components we have is the PDO and the volatile fatty acids. They both cause lung irritants as they go into the atmosphere, so they must be handled in a well-ventilated environment. Luckily, the PDO, glycerol, and PHA are not flammable because their flash points are over 100 degrees Celsius. The VFAs, like acetic acid, have flash points at 40 degrees Celsius, which is more dangerous. But luckily, our process, which has to do with culturing cells, do not really go above 40 degrees Celsius, and it's relatively dilute in the process, so it should be safe. And furthermore, we did a LOPA analysis using the risk analysis screening tool that's available on ACCI. So what it does is it takes our process equipment and all the information we put in for plant layout, and it calculates gas dispersion with like the ERPG ranges and chemical indexes to come up with some possible failure scenarios. And on the next slide, we will look at the risk summaries. So here's a chart of the risks that we analyzed for the LOPA. So for those who are not familiar, the x-axis is how severe an incident might be, 7 being the most severe. And on the y-axis is the frequency factor, so how likely a scenario is to occur. So you see the numbers 2, 2, and 3 there on the chart. That means there are 7 scenarios that we considered that were high risk, and we want to move them as far down in the scenario frequency as possible under the yellow highlighted boxes. So for our process, we decided to the LOPA found 2 significant scenarios that need safety protections or safeguards. One is that the potential for the production bioreactor to overfill due to a faulty sensor, and also the mechanical integrity of the vessel tank, so any leaks or holes that might happen. Yeah. So in order to mitigate those risks, we suggested having an operator present at every refill in case we need to shut off the process. And we also decided on a redundant level indicator inside the production bioreactor, which it's unlikely for two of them to fail simultaneously. And then also routine inspections of the equipment to ensure for the integrity. And as you can see, all the cases moved below the highlighted box.
All right, back to the money. So for our capital costs, we first had to size the equipment based off of our desired PHA production rate of 1,000 metric tons per year. And the cost of equipment came out to be around $3 million. And using the tables from our Capstone 1 textbook, we were able to calculate a fixed capital cost using the Class 4 estimate of $21 million. And then we also needed a warehouse in order to house all of this equipment, which we determined was going to be around $10 million. So total cost of $31 million. Here's our balance sheet at year 0. The key takeaways here are going to be the 7-year Small Business Association loan, which we hope to take out for $5 million at around 9%. We're also going to take a mortgage out of the warehouse that we're buying, 5 years, pay it off as quick as possible, leaving us with a shareholders' equity of around $16 million. And so for our prices, for the first 7 years, we're going to sell the PHA at market value, the lower end of it, or right in the center actually, of market value in order to pay off our fixed capital costs, the mortgage, the loan. And then after those 7 years, we're going to drop the price of PHA to 54 cents per pound, which is well below the prices of polyethylene and polypropylene. And we're hoping to really penetrate the market for those prices. So some important figures here. Because we're changing the price of our PHA as we operate, our income is also going to change. So for the first 5 years, it's going to be at its lowest. Then it's going to even out years 6 to 7, get to 2.4 million. And then once we pay off the SBA, and drop the price of the PHA, our income is going to stay roughly the same, at around 2.367 million, which is pretty decent. And then, so the ROE, because our income is going to be lower first 5 years, it's going to be an all-time low for the first 5 years. Years 6 to 7, it's going to spike, and then years 8 plus, it's going to even out. The WACC, weighted average cost of capital, is going to be around 9%, and our internal rate of return is going to be 12%, which is well above, not quite 350% these guys had, but will do. And the net present value after subtracting off the shareholders' equity is about $4 million.
So we're gonna kind of just wrap up our presentation, kind of just reiterate kind of our process and presentation. So we're looking into do a promising bioplastic production method that is feasible at our scale of targeted 1,000 metric tons of PHA per year and the 2,100 metric tons of 1,3-PDO per year. With that starting post-tax profit that Ryan just mentioned of $1.5 million and with a payback time of about 7 years. And that block flow diagram is just kind of to reiterate our process in simple terms, where you have the crude glycerol going into the fermenter, producing our VFAs, which will go to the PHA accumulation batch reactor where it meets up with the MMC from the SBR where it's been conditioned to produce our PHA and 1,3-PDO. And going forward, we're going to look at certain specific things. So the literature shows that there's proof of this working at a bench scale process, But before we kind of go into our 1,000 metric ton process, we would require pilot scale studies before moving forward to provide better proof of concept data and kind of have a better chance to look at the kinetics of the reaction. We'd also like to determine the MMC composition of local waste treatment. As Charlie mentioned before, the one that we found in research is based on a waste treatment center in Denmark, and Goshen, Indiana is very far away from Denmark. So we'd also like to look at alternative downstream processing. Currently, the plan ends kind of right where our PHA is produced, where we would lyse the cells in the PHA. We'd provide crude PHA, but if we're able to include downstream processing, we can probably provide higher quality PHA in-house rather than having to sell off the crude PHA and having a separate company kind of use it.
And so that concludes our presentation. Thank you for your attention. We'll now open the floor to questions.
Five, yeah.
Are there any questions?
Where's your raw material made, primarily?
So crude glycerol is primarily a byproduct of biodiesel production. And I think it's primarily like methanol is the main balance, as well as a little bit of ash.
The Gulf Coast. That's the answer. It's made, your raw material is made on the Gulf Coast. You start thinking about the cost of distribution from raw materials to Goshen, Indiana. I have actually been to Goshen, Indiana, and I have actually sold to Berry Plastics. The cost of distributing plastics is relatively inexpensive. Or you might want to reconsider locating a plant near your raw materials.
Okay.
That's far more expensive.
Gotcha.
And you also have customers all around the Gulf Coast who can consume these products.
Okay.
Yeah, I was going to ask you, why did you choose Goshen? What was the motivation for that?
Well, we had the PDO consumer, DuPont Tate, up in Midland, Michigan. Berry's Plastics was there. We were hoping to sell to them. Also, there's a waste treatment plant nearby. I know there's waste treatment plants in a lot of places. And my mom lives in Cleveland, so. Yeah.
Well, I was at Purdue University for a number of years, and there are advantages to work in Indiana, for sure, to setting up a company there. But if your main suppliers are going to be somewhere else, it's not really a good choice.
Are there any processing limitations you're aware of your finished products?
So the PHA, usually the way that they extract the solid biomass is through centrifugation. So we would...
I meant downstream. So you've made a finished product, you've sold it to someone who is going to make their product. They're either going to injection mold it, they're going to extrude it, they're going to make a film out of it, there's any, whatever places you imagine. Are PHA products efficacious enough to be used in high-speed plastics processing equipment?
So the uses that I'm aware of, they are able to be injection molded, and they can also be cut into current plastic products such as polyethylene and polypropylene to try and decrease the amount of the petroleum-based plastic that's being...
Do you have any sense at all of how much of the commercial market is used as a mix with polyethylene or polypropylene?
I couldn't speak to that currently.
I think they're trying to move away from that because when that biodegrades, it just creates micro-sized particles of those petroleum-based plastics.
And it would substantially impact the plastic manufacturing processes, which are usually very big, very fast.
So the polyhydroxyalkanoate is a polyester? Is that what it is?
Sorry, say that again?
It's a polyester? What kind of polymer is it?
Yeah, it's a polyester. It's a polyester. Because it's the, essentially all the acids convert into a PHA, but one of the main ones to look at is also PHBV, which is a polyester of the butyrate and the valerate together, copolymer.
Don't think we have the actual structure on the slide, but
Yeah.
PHA is kind of a class of.
PHA is kind of the overall class, and then each of the volatile fatty acids kind of converts into kind of into a specific polymer, which is overall known as a PHA.
Yeah, there's a structure. So and this material you said is a byproduct of the biodiesel industry?
The crude glycerol.
The crude glycerol.
Our feedstock.
The feedstock.
Our
The feedstock,
feedstock is a
Then it
byproduct.
polymerizes in your plant.
It's converted
Yes.
to VFA and then converted into rice.
Questions from the
Yeah, sure.
So is there a market, like, are people, companies in America actually using bio-based plastic versus all like polyethylene?
I know that PHA in particular has actually got a lot of attention in terms of surgical implants because it's very biocompatible. There's not really any compatibility issues. Other than that, it breaks down very advantageously. I think some of the other bioplastics can lead to like acidic environments when being broken down, but PHA actually breaks down into acetyl coenzyme A and another pseudo-enzyme type molecule that bacteria use in their respiration cycles normally. So there shouldn't be any like secondary environmental impacts such as like acidity changes, things like that.
Are there any like government like changes trying to move this like plastic industry into like bioplastics rather than just polyethylene?
Not
Just
that-
out of curiosity.
Yeah, not that we're aware of right now.
Yeah.
Any further questions?
Can I see your process again? Just one
Sure.
more?
The PFD?
So take me through it again.
Okay, so top left we have the fermentation vessel. Leads into a stirred effluent tank as we
So
want.
the fermentation does what in this process?
Fermentation takes the glycerol feedstock as well as some aqueous bacterial media, converts it down into the volatile fatty acids, so kind of like the precursor to the monomers and eventual polymers. That gets dispensed into an effluent tank that stores this as it's a continuous process and dispenses batch-sized quantities downstream. And after that, we actually have a settling tank to gather the supernatant, which will have the VFAs and the PDO, and we will dispose of the biomass that settles to the bottom just so that the process later on doesn't get too clogged up. That feeds into the accumulation vessel. At the same time, you have the bacteria that are conditioned in this SBR enrichment reactor that go to a settling tank. In this case, the biomass is what's important. So we take that and then dispense it into the PHA accumulation reactor. So with the conditioned biomass and then the VFAs and PDO, you end up producing PDO and PHA.
So, yeah, do you address the biosafety issues, the safety issues? But how about the biosafety? How are you going to decontaminate and so on? Do you?
So the main agent we're looking at right now is chlorine. We haven't gotten too specific yet as to the regime we would use for sterilization.
Also, downstream, the cells are lysed to obtain the product, so a majority of the living cells are dead.
Downstream, but upstream when you're actually setting up your
Yeah.
your reactors.
Oh, so at the CSTR and into, yeah, that's what Charlie, yes,
Yeah.
with chlorine.
So for that, we can also look to see what wastewater treatment does with any excess bacterial sludge they have. Like Charlie said, I believe the most popular ways of dealing with that are chlorination and I think decontamination with ozone as well.
Good. Yeah. Great. Thank you.
Just one last comment. Your pricing strategy. So I want you to imagine that you have gotten a customer to buy your product at 57 cents a pound, And 7 years later, you come back and say, I have some really good news, it's now $2.50 a pound.
Ours was, it's the opposite. We're 250 a
You
pound.
started 250.
We started
Yeah,
at
and then we're
250,
moving down to
Yeah.
50.